We're going to take a look at some literal equations, and the tools that you already have to solve regular equations are what we're going to use today as well. Literal equations just means that you have more variables, and we want to be able to rewrite the equation for a different variable. So this is really useful if you're doing sometimes word problems or formulas for something like geometry, but again, it's the same skills that we use when we're solving equations. So we broke it down kind of into two different kinds of problems. When you have just everything kind of written together with multiplication versus when there's addition and subtraction. So we'll start with the first type, which means everything's written together, it's all multiplied. So in this first problem, I'll give you a chance to write it down. It says D equals RT, and we want to solve for T. So I'm going to write this just a little bit bigger. And I'm going to set this up just like I would if I was solving an equation. I like to draw that line down my equal sign. And now our goal here is to get the T by itself. And so I think sometimes color coding will help you focus on what it is you're trying to isolate. And so if we want to solve for T or get T by itself, I need to move that R. The R needs to be on the other side so that T is totally alone. Right now it says R times T. So I would divide on both sides by R. Right, cool thing about literal equations is there's not a lot of times where you necessarily have to combine like terms or anything. So D divided by R, we're just going to leave as D divided by R. That does isolate my T though. So now I do have T by itself, which is what we mean when we say solve for T. So my answer here would be T equals D over R. Right, let's jump right into the next one. For number 2, we've got I equals, I'll make that a capital I so you can tell it's not a 1, PRT. I'm going to set it up again. I'll give you a chance to write it down. Draw that line down the equal sign so I make sure I'm doing everything the same on both sides. So, our goal here, it says solve for R. So this time, I want to get the R by itself. And I think these are easiest. Sometimes you can just do them in one step. So right now over there, I have P times R times T. So to move the P and the T, the opposite of multiplication would be division. I'm going to do them both at the same time. I'm going to divide by PT. And same thing on the other side. And just like the last example, we really can't actually clean up that left side much. We would say I over PT equals R. And so that would be my final answer. When I solve for R, I get I divided by or over PT. Right, and number 3 says V equals 1/3 BH. This is actually a volume formula, and we want to solve for B, or get B by itself. So again, that 1/3, the B and the H are all just being multiplied together. So if I'm trying to get B by itself, I need to divide the 1/3 as well as the H. And for a problem like this, again, I would just do them in the same step because they are both being divided, so we can do that together. So we're going to divide by 1/3 H on both sides. And that will leave me with just the B on the right side. Now we can actually clean up that left side a tiny bit. It's not wrong to leave it as V divided by 1/3 H. That fraction in the bottom, remember way back when you learned division by fractions, when we divide by a fraction, we actually flip it and multiply. So if I am trying to divide by 1/3, when I flip that, it would be a 3, and I'm multiplying. So I could rewrite this if I wanted to as 3V over H. So again, that's just some fraction simplification. We would say B equals 3V over H. All right, last one looks like it's going to be really tricky. It says E equals mc squared. That's one of those famous formulas I feel like everyone has heard of. And our goal here is to solve for m. We want to get the m by itself. So right now I have m times c squared. That exponent actually isn't going to make this problem any harder. I'm just going to divide by c squared. I don't need to get rid of the exponent to get m by itself, so I can leave it. So we would have E over c squared equals m. And we don't need to simplify that anymore. So literal equations do have a lot of letters in them, which can be a little tricky, but I do think you don't have to actually do as much simplifying, so they end up being a little bit less work. All right, our second type is going to be when we do have some addition or subtraction, and we've actually already done this in our linear unit when we were going from standard form to slope-intercept form, and we had to solve for one of the variables. We've done something very similar to this, but we're going to review it again today. And again, to get whatever by itself, we just use the same skills we would use if we're solving an equation. So if I have mx plus b equals y, that should look familiar. That's our slope-intercept equation. And we want to solve for x. If this was an equation, it's essentially a two-step equation. We would do the addition or subtraction first. We would move that. So minus b on both sides. That will leave me with mx equals y minus b. I can just write as y minus b. Can't do anything more than that. Those are different variables, so I can write them as an expression, but I cannot actually combine them. And then we're still trying to get x by itself, so I need to get rid of that m. mx means m times x, so I'm going to divide by m. I'm going to divide everything by m, and I'm just going to write it as one big fraction. You could do them as individual pieces. That would be the exact same thing if you wanted to. So we can write this as x equals, actually let's go back. I think you're more familiar with dividing everything by m. Let's do that for this because that will be helpful in some of these other examples. So we can write it this way where everything gets divided by m. We can either represent that with one big divide by m or each individual piece. So y over m minus b over m. And that would be my answer. And again, you could write that as just one big fraction bar with the m if you prefer that, but in these next examples, I think it might be helpful to see it this way for this first one. All right, in number 6, we have 7x plus y equals 15. And we're trying to get x by itself again. So just like our other two-step equations, we move addition or subtraction first, so minus y on both sides, which will give me 7x equals, and again, I can't actually do 15 minus y and simplify it because they're not like terms, so I just write it as 15 minus y. And still trying to get that x by itself, so I need to get rid of the 7. So I would divide everything by 7. So that will give me x equals 15 over 7 minus y over 7. And again, you could leave that as 15 minus y over 7 as one big fraction, but sometimes it'll simplify nicely, and this might be helpful. Like, for example, if you were trying to get y by itself to graph. So I'm going to keep splitting these up. So we've got x equals 15 over 7 minus y over 7. All right, here would be a great time to pause and try one yourself. When you're ready to turn it back on, go ahead and push play again and check your work. So this time, we've got 2x plus 3y equals 12, and we actually want to solve for y. So this is what you have done. You've gotten y by itself. And when we did that, we moved the 2x first. Keep using colors to show you what I'm doing. So we're going to subtract 2x on both sides. When we did this in our linear unit, because we wanted them to look like slope-intercept equations, we typically wrote the x first. We would write negative 2x plus 12. You can write it either way. It doesn't actually matter. We can just leave it as 12 minus 2x if you'd prefer that. And then my last step will be to divide everything by 3 because I'm still trying to get this y by itself. So I'll get y equals, and this is where having the division separate I think kind of helps. 12 divided by 3 can be simplified to 4, and then 2 divided by 3 is just 2 divided by 3, 2/3 x. So when we solve, we get 4 minus 2/3 x. And now this is an example of, we would want to do something like this if we were trying to graph this equation. We would have to get it in slope-intercept form and be able to graph. All right, last example, we've got 3x minus 4y equals 20. And we're trying to get y by itself again. So any addition or subtraction goes first, which means I need to move this 3x. Don't forget that negative sign that was in front of the 4y has to stay there, that minus sign. And I'm going to write this as just 20 minus 3x. Again, if you prefer to write the x first so that it looks like slope-intercept form, you can. And then I need to divide everything by -4. And let's clean up a little bit. So 20 divided by -4 is -5. -3 divided by -4 would be positive. A negative divided by a negative makes a positive. And I can just leave it as 3/4 x. And now that's something we could graph. We see the y-intercept, which in this one would be -5. And then the slope is 3/4. Make sure you go to class so that you can get some practice with this with your teacher. Thank you for watching.